All right, we're still missing a few people. We'll generally wait a few minutes to get everybody here as much as we can every day. But before we have everybody here, we'll talk about a few things.
Oh, she said you couldn't make it, remember? She had attendance today or something.
Oh, that's right. She did say that.
Is Packer coming later?
Yeah, Packer's not getting out early from school. I don't know what he has at the end of class, at the end of the school day. But
You want to go to the hallway and see if Cole's out there?
sure, if you like. Let's talk about this math. Okay. I did not email you guys back with the syllabus, as you may have seen. My night got kind of crazy busy last night, but I did post it on my Open Math site, along with a link to the class videos. So now if you click on the course syllabus, you'll get our course syllabus, and it has been slightly modified to reflect the summer. It includes the My Open Math stuff. That also includes labs and the grading and evaluation here. And so that's been adjusted. They also wanted us to include an academic honesty statement. I couldn't remember what they said in it. So I said, don't cheat or be dishonest. There's some better way to say that legally, I'm sure, but I don't really care. I'm just doing what I'm told. So the syllabus is available in My Open Math, and also the class video link should take you to a playlist. Here is the playlist. First class from yesterday is up there. Is yesterday the 15th, really? Yeah, I guess it was. That means tomorrow is my 20th anniversary.
Congrats.
Gotta remember that. Thank you for
Almost
that.
as long as I am old.
Yes.
So.
Yes, I have been married for a while now. So, and on that note, I will actually I'll be going to California next week, partially for work, partially for a little bit of vacation with my wife. And we will leave probably on Tuesday night, which means we won't have class on Wednesday. So we won't have a lab next week. We'll do our lab this week and we'll skip it next week. But it also means that we might have to go early on Tuesday or short on Tuesday, one of the two. It depends on when I can get a flight. I don't know when I'll be able to get a flight out of Denver. Right now it looks like the flight that's available is like at 6:45, which would just completely wipe this class out at this time. I don't know if there are any later flights available going to San Francisco or Oakland or San Jose. So it'll be kind of up to you guys. If you'd rather do a class, if we don't do a class at all that day, what we would do is I would teach the class remotely from California that day, or the next day, Wednesday. So we kind of have a couple different choices. We can either go early on Tuesday, or we can do a remote class on Wednesday from California, which I would teach from California. I could teach it live, and you guys could log in with your computers, or I could teach it and record it, and you guys could watch it as you please, either way, or both of us. So, kind of depends on what you guys want.
Tuesday I can't go earlier. I'm going to need to keep house or grass.
Okay?
I mean, I don't even know if I'm going to go.
Okay, so it may not matter to you one way or the other. So either way, we won't miss a class. We'll do it some way. We'll make it up somehow by teaching remotely or by recording it. But we won't have a lab next week since I will be gone. And then the next week we'll be back to our normal schedule. No, we won't. Because the next week, let's see. I have to look at a calendar. Let's look at a calendar. Calendar. Today is the 16th. Next week would be the 23rd. Let's see. Yeah, so the next week after that is actually Memorial Day, 29th. And I don't believe that we meet on Memorial Day. I believe that we take that day off technically. Hello, do we have someone here? Hi. Are you here for physics? Can you hear me?
Are you waiting on Cassidy?
I think so.
Okay.
This is for
we got
physics.
it, so.
This is for physics, right?
Yes.
Okay.
Hey, just a second, Jared.
Okay. Whoa, that's going to make me dizzy. You get a little tour of the Broken Bow extension right now. Hello.
Hi.
We are back in physics. We're going to be meeting in this room now, which is actually my physics room, because the other room is really messed up. I don't know what you're seeing right now. Are you just seeing me, or are you seeing my whole computer screen?
I'm seeing you only.
Me only? Okay, I will share my computer screen with you. So sometimes you'll be seeing me, sometimes you'll be seeing my computer screen. Now, let's see.
Oh,
Now
there
you
you
can
go.
see my screen, I assume?
Mm-hmm.
Okay, good. We were just talking about the additions I've made to the MyOpen Math site this afternoon. I think I'd made them, or this morning or something like that. And so the course syllabus is up there. I was going to email it to you all yesterday, but I apologize. I got a little bit busy. And then we also added the class videos link here. And both of those things are quite important for this class. If you click on the syllabus, it'll show you the syllabus. And you should read through it just in case you have any questions. Maybe I didn't cover things completely yesterday or something. Maybe I didn't discuss something you wanted to discuss. And if you have any questions, please ask. But then we also have the class videos. The video from yesterday is already posted up here. And I will post the remaining videos as we go. And speaking of videos, next week I will be leaving to California, and I will probably miss class Tuesday and Wednesday, which means we won't have a class on Wednesday. And on Tuesday we will meet, but, well, we will have a class, but we won't necessarily meet all together. Probably the best option for us on Tuesday is for me to record a class. Either I could record it before I leave on Tuesday, or I could record it Wednesday, and then you guys could all just kind of watch the class. And if you have any questions for the homework, you could email me those questions before the class, and then I could address those questions in that video for any homework that we're doing at the time. It should be chapter 2-ish, chapter 3-ish maybe, depending on how we're going here. So the other option that I'm not entirely sure would work for everybody is to meet earlier on Tuesday. So if anyone would prefer to meet, live on Tuesday earlier in the day rather than me recording a session, send me an email, and if I get enough people interested in that, I'll do that, and I'll record that and then make it available for everybody. So it's just kind of up to you guys. If you guys really want to meet on Tuesday and meet earlier before I leave to go to Denver and take a plane to California, then send me an email. Otherwise, I'm just going to plan on recording a video and answering all your questions that way. And then the week after I'm gone to California, the Monday, which is we were just looking at that, the 29th or something like that. Monday the 29th here, I believe is Memorial Day. So we are not supposed to have classes that day. I don't believe the buildings are open. So we will not have class on Monday the 29th, and we will come back on Tuesday and Wednesday and get things done here. So starting next week, we'll have a little bit of craziness, and then hopefully we'll be able to settle down into a nice rhythm and get things done. Any questions before we push on with all this stuff? No? All right. Well, let's go ahead and finish up covering all the stuff we need to cover in Chapter 1 and try to get it done as quickly as possible so we can talk about the homework and anything else we need to talk about. I would like to get into Chapter 2 a little bit if we can today, but we'll see how that goes. I believe that we were on Section 1.3. Oh, there we go. We already have somebody who's answered. I will. Okay, so I believe this is where we were at. So accuracy, precision, and significant figures. I'm going to try to move this little window a little bit out of the way. Okay. So accuracy and precision. These are two words that we use a lot when we're measuring things. And they are important. Don't get me wrong, they're extremely important and extremely valuable to understand this stuff. But if you're going into science or engineering, you're going to learn a lot more about this stuff in subsequent years. And in the time frame that we have and all the stuff we have to cover in this class, I try not to spend too much time on it. This is about as far as I'm going to go with this. These two targets with these bullet holes in them represent the difference in accuracy and precision. Does anybody know which one is which? You can kind of read it if you have good eyeballs.
Accuracy is the bottom line, precision is the top.
Okay. So accuracy is the bottom one, precision is the top. Okay. Anybody else have an opinion on that? What's that? No? It's actually, what did you say, accuracy is?
Accuracy would be on top and precision on top.
It's precise and it keeps you doing the same thing every time.
That's correct. So precision is the ability to repeat something, to repeat a measurement, to repeat a result, and to get the same answer every time. And so that would be the bottom one, where their bullet holes are not necessarily in the center of the target, but they're all close together, right? The accuracy is the top one, where they're all very close to the center, but they're very far from each other, right? So it's a low precision, those are low precision shots on the top, but fairly accurate, you know. But the ones on the bottom are actually less accurate, but more precise. And of course, ideally, you'd like to have both accuracy and precision, but in truth, you usually don't have either. You usually have mixed degrees of both. And so you have to understand the difference between them so you can understand your measurements. Now we can determine accuracy and precision just from numbers. We don't need a physical drawing like this. We don't need a graphical representation for this in science. And the way that we do that is by having a way of expressing our numbers, expressing the values of our numbers and the precision of our numbers and the accuracy of our numbers. And we use significant figures to do that, and uncertainty. So, first of all, uncertainty is a thing that a mathematical tool that we use, a statistical tool that we use to calculate our what we call it uncertainty, but it is actually going to calculate our precision. It's going to calculate how far off our numbers are from each other. Okay, so percent uncertainty is a precision. It's a measurement of precision or a determination of precision. And the way that you do it is you take all of your measurements, all of your numbers or whatever, and you you calculate how far they are away from each other, which is what this delta A is up in the top here. This little squiggly thing is called a delta. So this is the delta A. Those are all the differences from each other, or the differences from the norm, or the differences from the mean, or the average. It depends on how you're doing it. And then you divide it by the actual average. And it can be from an average, it can be from an average, or it can be from an expected value, or it can be from some other things. In physics, we'll generally have an expected value. So we have an expected value that we're trying to hit, and then we have all these differences from that expected value. So if we're trying to hit 5, and we have a 7, then the difference from that expected value was 2, positive 2. But you could also have a negative 2 at 3, right? From there. And that's what that delta A is all about. It's those differences from the expected value. And then you divide that by the expected value, and then you multiply it by 100, and it gives you a percentage of uncertainty. And that's how we measure that in the sciences. It's measured that way in the social sciences as well with statistics. This is a statistics tool. And from time to time in this class, I will be asking you to calculate that, so you'll need to kind of remember that and maybe bookmark that or something, highlight it or something. But here's an example of using that. We have this 5-pound bag of apples that we're measuring, and we measure 4 of these things in 4 different weeks, or maybe we're taking averages or something over weeks. But we have week 1, week 2, week 3, and week 4, and we have 4.8, 5.3, 4.9, and 5.4 pounds. And we want to calculate the uncertainty in these measurements. Well, remember that delta A is all these different differences, right? And so if we do this for, let's see, uncertainty. So in this one, they're actually taking the overall uncertainty and there are a couple of different ways that we're going to do this in this class. In this particular case, they're doing the overall uncertainty. So they're taking the maximum difference from the expected. So that's 5.4 is the biggest difference. So the maximum uncertainty is plus or minus 0.4 pounds. You have to go both directions. Even though you only have it in one direction, it's only going over by 0.4, you have to assume that it could go under by 0.4 when you're doing the maximum uncertainty. So then you use your delta A is that plus or minus 0.4, you put the 0.4 on the top, you divide it by the 5 pounds on the bottom, multiply by 100, and you get an 8% uncertainty, an 8% maximum uncertainty. That is the maximum amount of variation that you have in your measurement. No more than that. You could also have an average one, which is usually called a standard deviation, and it's also calculated in a very similar way except with an average. So anyway, and an average one is one that we will use later on in the lab, and we'll revisit this later. The other thing is the other thing we just talked about is the significant figures. So how many of you have ever worked with significant figures before in a class at all?
First semester, junior year for chemistry. We spent like 2 days on it, and then we worked on it again.
Yeah, and that's the thing that bugs the heck out of me. That's how most classes touch significant figures. They talk about it for a couple days at the beginning of class, and then they never ever use it. And that's because there's no real need to use it until you're actually doing experiments, real experiments. And so it's just kind of ignored, and that's why I don't like to waste too much time on it. We're going to spend 5 minutes on it, and then we'll be done. So significant figures are, the significant figures method is a way of tracking how precise your measurements are. So let's take the example of measuring with different types of units, okay? Let's measure, hello. Let's take, for example, let's measure this building, okay? So if we're going to measure this building, what kind of measuring units might we use? What would be?
Feet.
Okay, you could use feet, square feet if you wanted to measure the area. Okay.
If you're doing scientific stuff, you probably use meters.
Okay, we could use meters. Okay. Could we use millimeters? Sure, if we wanted more precision, right? We could use millimeters, we could use micrometers, we could use nanometers. If we wanted a lot of precision, we could do that. Yeah. But could we use kilometers to measure this building very precisely? It would be extremely imprecise. Well, unless we had a kilometer-sized ruler that had really small markings on it, right? Had meter-sized or millimeter-sized markings. We could do that. But then we're just measuring in millimeters, right? But if our measuring stick only had kilometers on it, what would the size of this building be? It'd be 1 kilometer or 0 or whatever you want to. I mean, it'd be undeterminable, really. We would have a very low degree of precision in our measurement. And this is how we use significant figures. We use significant figures to illustrate to the person reading our measurement how precise our measuring instruments and measuring techniques were. So if these measurements here on the page are all measuring in meters, what can you tell me about each one of these measurements? Which one is the most precise measurement of these 5? I can count. I'm sorry?
A.
The first one, right? Because they've obviously measured down here to this very, very small number of meters, right? And then this one up here is measured down to much less precision, right? So that can be very useful. Understanding how we use decimal places for this. This is actually more decimal places than anything else. However, you can learn even more if we use what we call significant figures. This second number, for example, has these 2 zeros on the end. Does that give us any information? Has a 0 here in the ones place and a 0 in the tenths place. In science, that means they actually measured 1/10 of a meter and got 0/10 of a meter. That means that their precision was all the way out to that point. Okay, so that's very telling. However, the zeros before the 9 don't tell us anything here. It just tells us they were measuring something very small using a small measuring device, right? So these are the ideas of significant figures. In this first one here, we only have one significant figure. We only know that their measuring device can measure in this smallest thing here, but not any smaller. And we don't know anything else about that measurement. You know, so this is at the 9/10 of a millimeter, right? 9/10 of a millimeter, or 900 micrometers or micrometers, and that's all we know about it. We don't know if it's 952 or 973 or 921. We just know that it's in the 900s-ish, and it could be even in the high 800s, and they round it up. That's possible too, because that's all they knew. That's all they could measure. It's kind of like this one right here is kind of like measuring the building with a kilometer. And so actually, while this measurement right here is measuring a very small thing, it actually is not necessarily all that precise for that size of an object. We would like to see a few more numbers out to the right to get more precision. Yes, sir.
So a number with ending in 0 would be considered more precise than a number less than 0.
A number that is ending, a number that has more numbers in it, which we call significant figures, and that's where I was just about to get to. So just hold the question for just a second. So this first one right here is measuring a very, very small thing, but is it necessarily precise? Because we only know one digit about it.
So we don't know whether it's precise.
The answer is it's actually not as precise as we thought. It's not necessarily precise. If we were measuring something bigger using that measuring technique, we could measure it more precisely, right? So precision is actually a little bit relative to the size of the thing we're measuring. It's not necessarily married to the actual size of the measurement. It's married to the number of digits that we can get in that measurement. So knowing that now, which one of these numbers do you think is the most precise? Which one tells us the most information about the measurement?
87.990.
87.990, there's 1, 2, 3, 4, 5 there.
We guess B.
B has 1, 2, 3, 4, 5, 6, right? Numbers to the left, zeros to the left don't tell us anything interesting, but zeros to the right do, right? How about this number right here? 6 times 10 to the third.
6,000.
Yeah, with scientific notation, it's a little bit different because we don't count any of the zeros that are in this 10 to the thing. Okay, we consider those to be blanks that we don't know about. So the only significant figure here is 6. It's the only number that's
That doesn't
significant.
get counted as a significant
Yeah.
figure there.
Yeah, all the rest of the zeros don't count.
Like if you have 869,000 and 869 are like the only ones that do that.
So that's a good question because there are rules about this. Where do the zeros count? Where do they don't? Where do they not count? So let's see if, I don't remember if they have the rules written down here somewhere. Let's see if they do. They don't, and that's fine. But the rules for significant figures are kind of like this. If the zeros are to the left of your first non-zero number, they're not significant figures. They don't tell you anything really about the precision of your measurement. If they are to the right of your last number and there is a decimal point, then they do count. So the significant figures in the second number B do count. The zeros rather in that B do count as significant figures. The zeros in D do count as significant figures. Any zeros that are to the right of your last non-zero number in a measurement that are not followed by a decimal point are not significant unless they are told to you that they are significant. Unless there is unless they actually write that these are significant. What's that?
That's why I have to.
So yeah, that can happen. So significant figures are a little bit tricky that way. And like I said, we're going to be done covering this right now and say goodbye to it forever. Well, not necessarily forever. We will see it again, but we won't necessarily worry about it much. And I think that significant figures are not graded in my open math at all. They want you to give you the number as you calculate it, and usually if you give it to 2 or 3 digits, 2 to 3 decimal places, if you have decimals in there, you're probably okay. Yes, sir.
Just so I can get it right down, would you be able to, like, with the significant digits,
The rules?
Yeah.
Okay.
Any non-zero number is significant, right?
So non-zero numbers are significant. Zeros that are between non-zero numbers are significant. Zeros to the right of non-zero numbers, as long as there's a decimal point out there somewhere, are significant. Zeros to the left are not. And zeros to the right that are designated or told to you that they're significant are significant. And they tell you something. So it's a little goofy. And essentially what it comes down to is a little bit of experience. You start to realize why this is as you get more experience with experimentation and experimental numbers. But we're not going to use it a lot in this class. Some physics classes just really hammer this over and over and over and over and over again. But I think it's to the detriment of understanding the actual physics. So I'm going to stop at that point unless anybody has any other questions. Anybody have any other significant figure questions or precision or accuracy questions? Yes, sir.
So if there's no decimal place, does that mean the zeros to the right are not significant?
If there's no decimal place and the zeros to the right are not designated specifically as significant figures, usually there's a note that says they're significant or not, then they're not significant. That's correct. What was your question, Cassidy?
Oh, I was doing the homework last night a little bit, and I went to that significant figures question, and I got it wrong because
we hadn't covered it yet?
Well, because I've done significant figures before, but since there was no decimal place at the end of it, the zeros meant nothing on the right.
Let's go take a look at it really quick.
It was
Because I can't remember what question
number 6.
what question I gave you there. How many significant
Mine's different
figures?
than that,
Oh yeah, every one of them is different here.
but that's okay. It's still the same idea.
How many significant figures does 33 billion 800 million liters have. So in this case, I would say 3. Let's see if I'm right. I don't know if it'll let me answer a question here. Yeah, it does. So I would say 3 there, and you have a different one. So let's go back and try a different one, because I get a different one every time I open the homework.
Well, mine was 5,140,000, and I put 7, but there was no decimal on the end, so
Yeah.
it should have been 3.
Yeah, that's correct.
Okay,
So,
thank you.
yep. Now, are these questions? These are giving you multiple opportunities to answer questions. Is that correct?
No, I got one that was question number 3, I got slightly wrong.
I don't think so,
Well, what's wrong with this homework?
because there's only one attempt allowed.
Well, let's fix that. It shouldn't be one attempt unless it's multiple choice, which, let's check. Let's see what the settings are. It's entirely possible I messed up the settings here. Well, yeah, put it as 1 attempt per problem. So I think that I've allowed 7 attempts per problem in the past, so that's what we'll do now.
There's also one question, number 3. I was putting them in order of the metrics, which I know that we're not. Well, we did go over that yesterday. And there's like a blank in it. There's a missing rank.
Okay, let me just get back to the homework again really quick here. So what was the other question you had about?
Number 3.
Number 3.
There's a rank missing.
Huh. On the left are the metric prefixes. Rank them from largest to smallest. And there's a
There's a
blank
dash,
one. That's
so.
goofy. What is the dash?
I don't know.
Hmm.
So I just wanted to let you know. Sorry, I didn't mean to sidetrack.
No, that's okay. Did anybody try this problem that has the dash in it?
Yeah, I did. The dash, I think, is just in
No, the dash is just 0.
Yeah,
It
dash.
represents 0.
It represents 0. So if you put that one as the smallest.
It's,
No,
the dash
It's
is
the middle one.
Oh, it's the middle one?
4.
Oh, okay.
Okay. I wonder why they do that. That's kind of weird.
And there's a chart. If you go back to the chart, it has 0, it has a dash, it has 10 to
In the book?
Yeah.
Oh, I looked at the
Okay.
chart, but I must have missed that scrolling through.
Okay.
So basically, you can only one.
Are the book links working for you guys?
Yeah.
I'm resubmitting everything in already.
So,
Okay, yeah.
I
It
see,
just shows
okay.
a dash.
oh, so
10
it represents 10 to the 0. I see. Yeah.
Okay. Sorry.
And this is good because, like I said, this class is being. I mean, you guys are a test group for this class, and so we need to rewrite some of these questions probably. And I will work on getting that done, writing these questions a little more clearly, making them more user friendly as we go. So
Thank you.
point out anything like that, and if there's any question at all that you think you understood and you think that you could have answered it correctly, if you just understood the problem a little bit better because of goofy things like this, just tell me and I can reset those and give you the proper credit and whatever else. So just send me an email. It's best if you send me an email so that I can fix them all at once because it takes me a fair amount of shuffling to get that done. So send me an email if you ever say, I did this question and I had the right answer, but I couldn't get it entered right. I couldn't figure out how to do that, whatever. And I will fix your grade, and then we'll try to fix these problems for the next class. So,
Mr. Bailey,
yes,
this might seem like an odd question. Do you even have an electrical adapter to switch it?
I do. How many do you need?
My mouse died.
No problem.
Thank you.
Okay. All right, so any other questions about that section on accuracy, precision, and significant figures? No? Are we good to go for that section? All right, let's move on to one of my favorite sections in the whole book. Approximation. So I have a great story to tell about this. When I started graduate school, I was working with one of my favorite professors that I had in undergraduate school. His name was Scott Bergeson. He was just a funny guy. He still is a really funny guy. He's a really interesting. He has like 12 kids, I kid you not. And at the time, I think he had kid number 10 when I was there. And he's a guy that you just look at and you think, man, he would make a great dad or older brother, because he seemed really young at the time. Now he's probably looking a little older because he's gray and everything else, but he's just a great guy. And we're downstairs in his laboratory, which is where I spend most of my time with him. It was in the basement of this building, two stories underground, 3 stories underground, in this dark pit. And we're doing these calculations on the whiteboard. And he's going along through these calculations, huge equations and formulas, and he starts approximating things. He starts saying, oh, that's, 9 is about 10, and, this 78, that's close to 100, so we'll just call that 100. And then he says pi. Well, pi, that's 3.14, that's about 1. That's close to 1. So he just rounded pi down to 1. But when he came to pi squared on the very next line, he said, well, pi squared is 10. So we had pi, which is 1, and pi squared, which is 10 in our approximations, right? Which I just always thought was really funny. Having a number itself being equal to 1 and the square of that number being 10 just made me laugh. But approximation is an extremely important part of all sciences. If you can learn to approximate very quickly and very efficiently, you can understand where your problem is going, where your problem solving is going before you even get there. And you can start to realize that you've made a mistake, that you're going the wrong direction, that you're totally off course, or that you're in the right way, you're going down the right path. And it's been very useful to me, not only as a researcher working for him and working for an engineering company that I used to work for, but also as a teacher in the classroom. I've looked at many a problem that I've been doing in class, or many example that I've seen in a book, and I've been able to tell right away if I'm looking at it wrong, thinking about it wrong, or if the book is even wrong. I've had to email publishers and say, you know what, that problem's wrong. And I noticed it first while I was in class, just doing an approximation in my head while I was working out the thing on the whiteboard, working out the problem on the whiteboard. So approximation is an extremely useful tool. We're not necessarily going to approximate pi equal to 1, but we are going to do some approximation right now really quick, the height of a building. So here is the approximation of the height of a building on campus or in your neighborhood, right? We're going to make an approximation based on the height of a person. We're going to calculate the height of a 39-story building. So the average height of a person, about how tall is the average human? 5'8"?
Probably close enough to 6 feet.
Okay, so 5'8", you could round up to 6 feet, and then metric, 2 meters. Now, how many of you know anybody that's 2 meters? I know that you do, because Caleb is over 2 meters. Okay?
Yep, you're right.
Right? How tall are you?
6'3".
Yeah, you're pretty close. 2 meters is about, 2 meters 10 is, I think, 6'11". And so 10 centimeters is about 5 inches, so about 6'6" is about 2 meters, 6'5", right in there is about 2 meters. So you're pretty close. You're about 196, 195 probably. I'm about 178, I think, or something like that. Is about 5'10". I can't remember exactly what it is, but I think it's 178. And so 2 meters, close enough. We round to 2 meters. But that approximation seems ridiculous because hardly anyone really knows people that are 2 meters tall. I mean, 6'5" is pretty tall, and very rarely do you meet people that tall unless you're around a lot of athletes. Sometimes you have a guy like Caleb who's not athletic, but is 6'11" or whatever it is. Yeah, Mr. Cooper's pretty tall. I had a student here who was 6'9" or 6'10", and he just hated sports. And I'm like, man, I wish I was 6'10". If I was 6'10", I would have played volleyball at the collegiate level. But even if, especially the vertical, I mean, guys that are 6'10" never have a vertical close to 30 inches. And, you know, at 5'10", at 30 inches means nothing. But at 6'10", it means something incredible. But anyway, anyway, the point being is that we've made this approximation that seems ridiculous, but it's going to help us. About how many people can stand on top of each other on the floor of a building? Well, in this particular approximation, they're going to use that as their measurement. They're going to estimate that about 2 people can stand on top of each other and reach the ceiling of each building. And in this room, you kind of get a feeling that that's not exactly true, because this room has pretty high ceilings, and most buildings do have much higher ceilings than we realize, because they have a lot of space up above the fake ceilings. So you could even say almost 3, but we're going to approximate 2 like them. And we're going to say that we're going to make a conversion of 2 meters per person and 2 persons per story. Notice that those are conversion factors. And then we're going to multiply by 39 stories to get our height. So it ends up being 2 times 39, 156 meters, right? And if I was doing this and I was approximating, I would even take out the 39 and turn it into a 40, right? Then you have 2 times 40, which is 160, which is just as good an approximation as 156, because we certainly don't know. This approximation is actually using a precision that we don't have. It's suggesting that we know the height of this building down to the meter, but we certainly don't with this approximation. With this approximation, we'd be lucky to get within 10 or 20 meters, right? We might get within 10 or 20 meters of the actual height of the building. So I would say not 156 meters, I would say 160 meters. I would round up. 160 meters is a much better approximation for this approximation. But using this technique, you can do a lot of things. You can you could measure the thickness of a $100 bill, couldn't you? If you knew, you've seen the stacks of bills that they have in the bank or in movies or something. You know, it's about 1 inch thick, and if you know how many are in that stack, then you can figure out the thickness of a bill. It's about 1 inch thick, and I think they put about 50 in a stack. So how thick is the $100 bill? 1/50 of an inch, which is not exactly true. A 50th of an inch is definitely not the thickness of a $100 bill. So it must be either a smaller stack or more bills in it. I just happen to know that a 50th of an inch is much thicker because I was a machinist. So, so the stack is probably not 1 inch, because 1 inch is about this big, and those stacks are probably about half that. And there's probably more bills than 50. There might be 100 in there, and that's much more reasonable. So getting down to 1/100 of an inch or even smaller, that makes more sense from my machining experience. But still, you can get in the ballpark, and that's what approximation is all about. If you were doing your math problem of what is the thickness of a $100 bill, and all of a sudden you were coming up with answers that looked like 1/8 of an inch or a 20th of an inch, you'd really know you were off if you did the approximation. So it can be very helpful. Okay. Now, here they're doing that one actually. Oh, they're doing a different one here. The bank stack contains $100 so it is 100 of them. 100 $100 bills worth $10,000. How many stacks make up $1 trillion, right? So what is $1 trillion? 10 to the 12th, right? So they're doing that. They're taking the volume of a stack, and they're calculating the volume of a stack in inches cubed, and then they're going to stack these up on a football field or something like that. Let's actually read the problem. I always forget to read the problem. So we have a federal deficit in 2008 was greater than $10 trillion. It's a lot greater than that now. But we don't have enough how much this is. $100, 100 stacks. So if we made $100 bill stacks and use them to evenly cover a football field, make an approximation of how high the money pile would become. So we're gonna approximate the size of the bill, about 6 inches by 3 inches by about ½ an inch for the stack. So it is a lot smaller than I was saying before. And then we're going to calculate the number of stacks by saying 1 times 10 to the 12 is $1 trillion. We're going to divide that by the $10,000 per stack. That means we'd have 1 times 10 to the 8 stacks, which is 100 million stacks of bills. 100 million stacks of bills has a volume, or well, let's see, they're going to do the area first. So it's going to be 5,000 square yards to cover. And then they're going to calculate 6,480,000 square inches and convert that into yards. And when they convert into yards, they get 8 feet thick. So 8 feet of $100 bills. That's a lot. Now it's like, 70 feet or something. And next year it'll be more, and the year after that it'll be more. Anyway, so they do another one here. They do some other examples here in the homework of cells in the body, bacteria in food, or whatever else. So lots of different things. But it's a useful tool, suffice it to say. So that takes us to the end of chapter 1 and allows us to get a little peek into chapter 2. Now is the time when we can ask questions about the homework. We've already done a little bit of that. This thing keeps moving out of my way here.
On question 2, it says convert PG to the standard unit. I couldn't figure out what PG was.
Okay, so P is a,
Is there combination?
so G is grams, and P is a prefix. It's one of the prefixes. There's, I think that one is, I think P is pico, is it? Isn't it? It's not pita. Pita is, pita is capital P, isn't it?
Picometers are small p.
Yeah, picometers are small p, and capital P is the peta, whatever.
PETA.
Yeah. Excellent. Can you hear all of us over here in North Platte, or just me?
I can kind of hear them, but they're really quiet.
Okay. The reason for that is that the microphone is at my computer up here. What I will try to do, is I will try to rig up some microphones and see if we can get better sound in the subsequent classes. I think I can do it. It'll take some work to do, but I will try to do that in future classes. All right, so that answers that question. Okay, is that
Yeah.
working for
I
you?
didn't figure out what it's all about.
Any other questions that anyone wants to review? Take a look at?
I think that the internet is not working here now.
The internet's not working in here?
No, I want to check if you're wrong with mine. If you want to check the gas.
It was very clean
Yeah.
earlier.
Just, use the visitor one all the time.
I was following along with the lesson
Oh,
in the book, and it was working fine. But
Okay.
it just randomly stopped.
the problem in this room is actually my fault. I actually designed this room to, I was allowed to design this room the way I wanted to, and I asked them to put metal mesh in the walls because I wanted to be able to turn it into a vacuum, or not a vacuum, but a microwave chamber, and reflect microwaves off the walls. They ended up putting the wrong mesh in the walls, so it doesn't do what I want it to do, but it does block signals poorly. I mean, it doesn't block them completely, but it does cause a little bit of problem with signals. Sometimes you'll get a good cell signal in here, sometimes you won't. Sometimes you'll get a good Wi-Fi signal, sometimes you won't. So I would use the visitor one because it logs on and off automatically. You won't have to type anything in. So they'll just kind of keep you logged in all the time. So, and if you have a cable, you could actually hardwire your computer in. You could unplug my cable from the back of that computer up on the desk. That Apple on the desk has a network cable on the back of it. That's the gray cable on the right side of the computer. Or you can use the computers on the desk. You don't even have to bring your own. All those Macs work and are good computers. So.
Maybe it's not the same computer, but I have one of my
All right. Any other questions for homework 1? Are we pretty much done with homework 1? Satisfied with what we've accomplished?
Okay. On question 10.
Question 10.
I'm sorry, I haven't had a calculus class for like 3 years, I guess.
Question 10 is the scientific notation.
Oh, yeah. So that one is just 6.3. I was wondering how to type it in the system.
Okay, so in this particular one, scientific notation, you take the first number, 8, and then you do a point, and then all the rest of the numbers, 5, 3, right? And then you just pretty much count the zeros after that, right? So
Yeah.
your zeros are 1, 2, 3, 4, 5. So you're going to do times. You use the time signal, and then 10 to the 5, right? Now I think that should work.
I think it'd be a 7.
If you click on that
Oh,
yellow
you're right. Sorry.
side, it'll tell you how to use it. If you click on that
Alright,
mark,
here we go.
Yeah, sorry. You're right. You don't just count the zeros. You have to count all the way to your decimal place.
here.
So it's 1, 2, 3, 4, 5, 6, 7, right? So it's actually not 10 to 5, 10 to 7. And I think that will give you the right answer. Let's check it. Yeah, it does.
Okay, that's when you write the 2 to the.
Yeah. So and there is that little tool there that you can use. Let's see if I can find another question with it. The little tool here to the right will tell you. No, that's not right.
It's the blue. It's the thing below where you get more.
Oh yeah, this one right here. Yeah, there we go. So, and anytime you have a question about how to enter things in, you can email me and I try to get back to you as quickly as possible. I don't remember who it was, somebody emailed me with a question last night and I was able to answer fairly quickly, I think. So, I try to stay checking my emails until a reasonable time at night. I don't stay up too late, but I don't go to bed all that early, and I try to check my email right up until I go to bed. And even when I'm out and about, I usually try to keep my phone with me so I can check those emails, because you can do my open math from your phone. I don't know if you've discovered that, but you can access it from your phone and you can work on it from your phone. So try to do that as much as I can.
On question 14.
Yep.
Is it? I don't remember how to look for that.
Okay, so this is a geometry question. And I like to put a geometry question in every once in a while just because it helps us to remember a few things that we might use from time to time in this class. This is a question about similar triangles. So similar triangles are triangles that have the same what?
Angles.
It's the same angles, right?
Same angles, yeah.
They have the same angles. That's the definition of similar triangles. Now, the results of similar triangles, or the theorem that has been proved about similar triangles, that they have the same proportions as well, that their sides have the same proportions. So with these particular triangles, because they're embedded within each other, and these two lines are parallel, which we assume that they're parallel, and they are. And that probably should be stated in here. They don't state it, but they should. Then we can say that these angles over here on the right are the same. These angles on the left are the same. They're of course sharing the same bottom angle. And then the sides will be proportional. So we have a side here that's 30, and a side that's 70, and then a side that's 15, and a side that's unknown. And when things are proportional, you can set up a proportional mathematical statement, which is essentially ratios, right? So you can say 30 to 70 equals 15 to x, or 30 divided by 70 equals 15 divided by x. Or you can say x divided by 15 equals 70 divided by 30. Either way. And then you solve that equation.
Which ones are equal though?
So it's the proportions that are equal. So you take the side of the big triangle and divide it by the side of the small triangle, and that proportion will be equal to this other side of the big triangle divided by the side of the small triangle. So big over small equals big over small.
Okay, so like for instance, in that one, it would be 30 over 70.
It could be 30 over 70 equals 15 over x, right? And we can go ahead and do the math really quick. Let me switch over to my, I often use a program called EduCreations when I'm doing a class like this, and every once in a while, if you ask me a question that requires a lot of visual explanation, I will use this website, and this website is free. If I start using it to send you lessons, then I will give you a sign-on for it. Otherwise, we'll just use it in class until that time comes. But it's it's an online whiteboard where I can record my voice and my movements, and you can see what I'm doing. So in this case, we have our triangle, right? And then our embedded triangle, which is somewhat smaller. I think theirs was the other way up. Theirs was upside down. Mine's upside down. But we have x here, we have 15 here. I can't write with my mouse very well. We have 70 is this long one. You know how long I spent trying to learn how to make this shape when I was doing math in high school? I spent like hours trying to learn how to do that. And then we have this smaller one, which is 30. It tells you how much of a nerd I was.
I can always get one side, but I can't get the other.
Yeah, and I can only do it. I can only do like this one, but this one always ends up funky, like that. Yeah. But anyway, so point is, I can do one side fairly consistently, and the other one gets really messy.
So you do 30 over 70.
So then we get it can be 30 over 70 or 70 over 30. You can do big over small or small over big, but you have to do it the same way on both sides of the equation. So in this case, we're doing the small side over the big side. That means we have to do small side over big side, or small triangle over big triangle over here. So that has to be 15 over x. And do you know how to solve a proportional equation like this? Yeah, you can use the cross multiplying trick, in which case you would get 30 times x equals 15 times 70. Right? And then you divide both sides by 30 and you get your answer, right? Okay?
And then with the 15 must be asked for the same thing I have it.
So yeah, this is a very similar question, and this one is much more related to actual physics. So we have a building that's casting a shadow, and then a stick that casts a shadow, right? And we know the length of the stick, we want to know the length of the building. So let's go back to our whiteboard, and let's take a look at this example. Whoa, that's a nice building. Let's draw a nice straight line. They should have a shape drawing tool on this, but they don't.
So then you just go 1 over 1.
So there's my building, there's my meter stick, right? And both of them have a shadow. The shadow of the meter stick is so long, the shadow of the building is so long, but these triangles are going to be similar triangles. So the angles are going to be the same, the proportions are going to be the same. This is 1 meter, this is 21 meters, this is some height, and this one was whatever it was, 0.7 meters or whatever it was. Sure, whatever it ended up being. But you would set up the proportions the same way. You would set up big over small or small over big, either way you wanted to do it, and solve for the you can do it that way. You can also set up this short side over this long side and this short side over this long side. Proportions work just about any way you want to put them together. And those kinds of little tricks that you remember from geometry from years ago, and trigonometry from years ago, we're going to get a lot of exercise using those things. We're going we're going to get some experience with them again, get them back in our heads and remember them, and we will use them quite a bit. So
How many decimals should I round to?
I would round to, you know, if you have 2 or 3, I would go ahead and get those in. Yeah, 2 is probably fine for this. I don't think it'll give you any trouble if you put in more. But every single one of these online programs for math has its little quirkinesses and has it. They each have their advantages and disadvantages. And the last 3 that I've used, of the last 3 that I've used, 4 that I've used, I think my Open Math is almost as good as any of them, but it's free, which is the real beauty of my Open Math. Because the other ones cost 40, 60, and 120 progressive, each one of them, for a semester. So they get pretty expensive. And the $40 one's not bad, but it's not, well, it's actually only 25. No, it's 40 now. But it's $40. It's not a bad program, but it's not great. It's not as good as this one. It's got a lot of quirkiness to it. So does anybody else have questions in the homework they want to do, or no? We're good? Okay, so it is 4:38. I've been here for 1 hour and 8 minutes. Let's try to get some more done in about a little bit less than an hour, and then let's call it good. So we're moving on to kinematics. Let's go. One thing I hate about this Zoom thing is it brings down this goofy toolbar. Okay, so let's go back to our homework really quick. I always like to look through the homework a little bit before we start, just so we can see what we've got ahead of us. So this one has 23 problems on it. The last one had a few less. And these problems are a little more difficult. There's a little more calculation. And some of them are graphical things where we have to look at a graph and analyze what's going on, figure out what's going on. Some of them have multiple parts to them. We're starting to use formulas now. We have pictures that go along with these problems to help us to understand. One of the things I really want you to know about physics is that visual representations are hugely important. And that just reminded me of something else I need to tell you, which is probably even more important at the moment. So anyway, these are the kinds of things that we're going to be dealing with here in this next chapter, and I like to preview them before I start. Now, before we get on to the next chapter, I got to take a little bit of an aside and talk about Physics 2410, it's called. You two are both going on into engineering, right? Cassidy, what were you thinking of studying? I can't remember.
I'm a biology major right now for pre-medicine, but I'm going to school for radiography.
Okay, so pre-med and radiography, biology, I don't think any of them require physics with a calculus base.
No.
So I think you're good. But if you're going into engineering, you do have to have calculus integrated into your physics, which means that you will eventually, not necessarily right now, but eventually you will need to sign up for my physics calculus course, which is just an addition to this course. It adds on a few homework problems for each chapter, not even every chapter, just a few of the chapters, maybe 10 of them or 12 of them. So for 10 or 12 of, not even 12, it's got to be 10 or 9 even. You'll have 10 or so extra assignments that have a few problems each in them. When I mean a few, I mean usually 5 or less. And those problems are concentrated more on the calculus behind the physics than just the algebra. You're doing the same kind of stuff, there's just going to be a little bit of calculus on them. You might do some derivatives or some integrals. Now, have either of you taken calculus already? You have? And
You're in the same class.
You're in the same class? Calc 1, Calc 2, both?
Just Calc 1, then Calc 2.
Okay, so just Calc 1. So Calc 1 will get you started in that class, but it won't get you finished. You really need to have Calc 2 under your belt as well, or at least started. You need to at least have started Calc 2 to really get done with this calculus class. So what I would recommend to you guys, now you're just graduating,
Yeah, I graduated from
heading to UNL, and you're just finished your junior year or just starting?
Just finish your year.
Just finishing junior year. So what I would recommend for you is to just wait until next year and take that class, and just take it because it's just an independent study on class online. So just sign up for it in the fall or in the spring whenever you have time, or you could even do it next summer. Then you would get a little review of physics, and you'd have a little calculus in there as well, and you'd be able to finish that up about the same time you're finishing Calc 2. For you, since you're going off to UNL, you can do the same thing. You just have to remember to do it, because you don't want to wait too long and forget physics and then have to take it later. So you can do the same thing, but just don't forget. Sign up for it in the fall and do that.
If I remember correctly, the way they have their engineering program is very structured. Like they have a pamphlet that basically says, here's your schedule, no matter
Yeah.
what you're doing.
Yeah, but you can sign up for my class at the same time.
Okay.
You can be dual enrolled in 2 different colleges, and they won't even know. They don't care. First of all, they don't know, and so it doesn't really matter to them that you're taking a class somewhere else. And it would just be literally an independent study. You just do it as you have time. You're just going to finish up 10 assignments and be done with it, and then those 2 classes together will transfer to UNL as a complete calculus-based physics course. Okay. Now, if you want to get that done before you leave, you could sign up for it this summer. It is available in the schedule, and I could help you through the parts that involve Calc 2. It's just kind of up to you if you want to try and crank it out before you go to UNL.
I looked on the website and it didn't say that you guys had a Calc 2 course available over the summer. Otherwise, I would have considered signing up.
I've tried to convince them to offer calculus in the summer, and nobody wants to teach it. I've offered to teach it myself, and they don't want me to teach it because I teach a lot of courses in the summer, and they try to reserve the calculus courses for the full-time math teachers here, and I only teach math part-time. So they try to reserve those calculus courses. So they just fought against me on teaching those over the summer. Hopefully, eventually, I will get them to do it, but they've never done it.
So between this class and if I were to take the calc-based physics with you as well, then it transfers to UNL as a calc-based.
It will transfer as a calculus-based physics course.
And it will satisfy the requirement.
It will, yes.
And it needs to like add rock data.
You can add that anytime. You can add it.
It's one online, so
Yeah, it's an online course, and it's essentially an arranged course, which means it's independent study. You sign up for it, and then you meet with me. I show you what to do, and you go off and do it. And if you have any questions, you just come in and we talk about what you have questions about, and I can teach you what you need to know and whatever else. But it's just kind of on your own, and when you have questions, you come to me.
how many credits is it?
It's 1 credit. Yeah, that's why it's just a few homework assignments and you're done. It's a 1 credit class. It's just an add-on to this course. So, yes, sir.
So do we have to go down to different people and sign up for it?
Yeah, you can do that, or you can do it online, and you can wait till fall because you can do it next year during the school year.
Well, I don't really want to do it in the fall because I already have a ton of
Okay.
classes.
That's fine. You can do it this summer as well. That's totally fine with me if you guys want to do it over the summer. So it shouldn't tax you too much. You're going to learn a little bit more. You're going to learn some things a little bit differently in the mathematics. So you'll have a little bit more homework to do, but it's certainly doable. Okay. Enough for that. Enough of that. Let's move on to chapter 2. Yes, the American kestrel. It's a really pretty bird. Have you guys ever seen a kestrel?
No. Where are they found?
Oh, all over. I believe we have them in Nebraska. I think I've even seen them in Omaha or Lincoln. But they're just a bird of prey, beautiful kind of hawk. We're going to be studying movement, kinematics. Kinematics is the study of movement. It's often also referred to as Newtonian dynamics or Newtonian mechanics. And we start off with very basic stuff. Where is something? Where is it? Where was it? Where will it be? Position, displacement. and we make definitions of these things, and then we use these definitions to move forward in the mathematics to define things like speed and velocity. Is there a difference between speed and velocity? We're going to learn about that. And why is this so important? In physics, we have a tendency to teach the material from a historical perspective. In many sciences, that is not the case. In many sciences, they teach you the latest and greatest from day one. In physics, we teach the very basic, the very fundamental from day one. We go to the nitty-gritty, and we teach you. It's like baby steps, right? You ever seen the movie What About Bob? If you haven't seen the movie What About Bob, I highly recommend it. It's a very dated movie from the 90s, but it's Bill Murray at his greatest. This is probably his best ever movie, and really funny. But it's baby steps. We want to take you down to the very lowest level of understanding and learning, and build from there, so that we're all learning things the same way, and we're all defining things the same way, so that when you talk to a physicist in Bangladesh, they're talking the same physics. You're not communicating, you're not struggling with language barriers and physics barriers. You want to minimize the barriers, so you want to all get your physics the same, and then you only have to worry about your languages. So we start basic, very fundamental. Position. What is position? I'm going to ask many questions like this during the class, and the questions will confuse the heck out of you, and I hope that they do, because it leaves an impression. Where are you? Can anybody answer that question? Where are you?
It depends where your starting point is.
Yeah, it depends on what's your point of view. What's your reference frame, right? We often want to say, well, I'm in North Platte. Well, okay, let's talk precision then. Where are you in North Platte, right? Yeah, Mid-Plains Community College, and if you left it at that, we got 7 campuses, right? All spread across Nebraska from Valentine all the way down. Valentine's north, right? I always forget where Valentine. I always mix up Valentine and Imperial. I don't know why. But anyway, Valentine all the way to McCook, and we got these things all over the place.
You could eliminate all the two.
That's right. We could say North Platte and Mid-Plains Community College, and that gets us into a 3-mile radius. And so we have precision involved, but we also have point of view or perspective or whatever you want to call it involved. But in reality, we're always moving anyway. The Earth is spinning; it's going around the sun. The solar system is rotating around an arm of the galaxy, and the galaxy is expanding away from the center of the universe. Everything is moving, so it is very, very much a trick question. Where are you? And so Descartes, French philosopher, mathematician, physicist, René Descartes fixed this for us. He said, you know what, if we define a coordinate system, and we assume that coordinate system to be fixed, we assume that it's not moving, even if it is. We just assume it to be not moving. Then we can say where things are. And he's the guy that invented the Cartesian coordinate system, the rectangular coordinate system. You have the x and the y and the z, or the r and the theta and the phi, or whatever you have. And then you have an origin, a beginning point. Where are you measuring from, right? If you have a Descartes system like that with 3 dimensions, how many numbers do you need to tell where anything is? Just 3. And that's what Descartes, that's the genius of Descartes. You need 3 numbers. You need, up, down, sideways, and in and out, or left and right, or whatever. 3 different dimensions. X, Y, Z, whatever. And it's a beautiful thing. And so we can describe position that way. How are we going to describe when we go from one position to another position? Yeah, we're going to call that displacement. And that's what this definition is right here. We're going to have a position that we started at, a position that we end at, and we're going to take the ending position, which in this particular definition we call x final. And in this case, we're only talking about 1 dimension. We're going to simplify down to just 1 dimension, and we're going to call it the x dimension. So the x displacement is going to be delta x. This is capital delta. We saw a lowercase delta before. They're just Greek letters in the alphabet of the Greek people. So delta x is going to be defined as the final position in x, or the final, that final coordinate in the x direction, and we're going to subtract off our initial one. Now in this book, instead of using an I for an initial point, they use 0. So this is called x sub 0 or x naught. X naught being an old-fashioned way of saying 0.
Wouldn't that be like your X origin or something?
That'd be your x at time equals 0, is essentially what that is referring to. So this will be your x at a final time and your x at your 0 time. And then you have your displacement. Okay? Now, what is the displacement between North Platte and Kearney?
98 miles.
Another trick question. Is the road to Kearney that you drive that takes you 98 miles to drive on, is it in one dimension?
It's in two.
It's actually in 3.
Well, yeah.
Because Kearney is lower than us by a couple hundred feet. It is actually the town of Kearney, the main town of Kearney, is probably about the same level as us, but where the freeway hits Kearney is a little bit lower than us. And so that's one dimension, right? The freeway turns left and right. That's another dimension. And then we have to move from here to there. That's your third dimension. So it's actually three-dimensionally, it's in 3 dimensions. And this is talking about 1 dimension, right? So 98 miles is a curving, bending, up and down road of distance, whereas this particular displacement is not that. It's a straight line. This is gonna tell you the exact distance between 2 points, the shortest distance, right? And so displacement is not necessarily the same thing as distance. The distance that we travel to Kearney is 98 miles. The displacement between here and Kearney is probably a little bit less than that. Okay? So displacement and distance, and those are important things in physics. Because let's say the sport that I did in high school was swimming. And in swimming, we were always swimming laps. And laps mean a very different thing in swimming than they do in other things. A lap in swimming is from one side of the pool to the other side of the pool. That's 1 lap. In track, you have to go all the way around and end up where you started to do a lap. And that's what most people call laps. So in swimming, we did 2 laps, and that would get us back to where we started. 3 laps would take us to the other side of the pool. And 5 laps would take us to the other side of the pool. Odd laps always took us to the other side of the pool. And if you did an odd number of laps in a 25-yard pool, which is your normal short course pool in America, then your displacement would be 25 yards. Even if you did 27 laps. 27 laps in a 25-yard pool is a heck of a lot longer than 25 yards. So the distance that you swam was a lot longer than the displacement of the swimmer at the end of those 27 laps. However, if I did 4 laps, what would make my displacement in the pool? 0. My displacement is 0 because I came back to where I started, right? So anytime in physics, when you come back to the place where you began, the position that you started, your displacement is 0. But the distance that you traveled is not necessarily 0. So there's your difference between distance and displacement, right? Here we have the example of this teacher, and I can't imagine who was the fashion designer for this teacher. You have the dark pink, tell me if I'm wrong, but dark pink with salmon and hot pink shoes. Just doesn't go. I don't know. I could be wrong, but that wouldn't fly if I wore it. Of course, I'm not a spring person, so I don't know what I am, but against that green background, it's just terrible. But anyway, she's walking here from the 1.5 meter mark is her x sub 0, and her 3.5 meter mark is her x final. And if you take the 3.5 and you subtract the 1.5 for your displacement definition, then you would get 2 meters of displacement in the x direction. And it's a positive 2 meters because she went from the left to the right. If she went from right to left, then her x final would be 1.5 and her x initial would be 3.5. And these two numbers would be reversed and you would get negative 2 meters, right? So displacement actually has a negative or a positive associated with it as well. It depends on which direction you're going in that dimension. Does distance care about direction. Distance doesn't care.
So it's always positive.
Distance is always positive. Displacement can be positive or negative. And here we get to a point in the discussion where we talk about different kinds of things that we measure. In physics, we often measure things that only can be positive, or measure things that can be either positive or negative. And this is the first encounter that we're having with that. Distance is only positive, displacement is positive or negative. And the reason for that is the idea of the vector. A vector is a mathematical construct that we use in physics and engineering to demonstrate things or to represent things that have more than one property to them. So in the case of displacement, displacement has two properties to it. It has a distance that you traveled. Distance is part of displacement in a way. So a straight line distance is part of displacement, but it also has a direction. So it has two properties associated with it. And so we call it a vector quantity because it has these two qualities that are associated with it. Direction and the number part of the quality, which is the 2 meters in this case, we call that the magnitude of the displacement. Some people like to call it the distance, but it's really only the straight line distance, or as the birds fly, as the crow flies distance. But displacement does have a magnitude to it, which gives you a value, and it has a direction to it, which makes it a vector. And we could use an arrow to represent this. If we were going to use an arrow, it would be this arrow right here. Right here in this picture, this arrow would be our vector. It goes from the 1.5 meter mark to the 3.5 meter mark, and it has an arrowhead on it which points in the positive direction. So that is our displacement vector. Here's another example that's a little more convoluted. We have our, this looks like our, this passenger must be in business class. He's traveling in a suit. But he's walking on the plane from the front of the plane to the back of the plane to get a magazine. And as he makes as he travels that distance, he's apparently going to be going in the negative direction because our coordinate system is set up so that x positive is pointing to the right. Every time you set up your coordinate system, you have to choose where your origin is going to be and which direction positive is going to be. Positive is indicated by the arrow on the different coordinates. Right? So positive is up in y. Here, the positive is to the right in the x. And since he's traveling from this part of the plane back towards this part of the plane, then this vector is going to end up being negative. He's going from the 6 meter mark, which is his initial point, to the 2 meter mark, which is his final point. So in this equation, you're going to have 2 meters minus 6 meters, which will give you negative 4 meters. So his displacement is negative 4 meters. But what if you're outside the plane and looking at him walking through a glass plane?
He's positive because he's actually moving.
Yeah, because the plane is actually moving much more quickly forward. So he'll still have a positive displacement according to somebody on the ground. So they have a different coordinate system. Their coordinate system is nailed down to the ground. His coordinate system is nailed to the plane. And so you get these different coordinate systems that can be relative to each other. And this is your first look into relativity. This is exactly what got Einstein thinking about his theory about relativity.
So, like, him compared to the rest of the passengers, when he takes those however many steps to go 4 meters back, his displacement is still going to be positive to someone who's on the ground. It will just be slightly less.
Yeah, it'll be
But on the other hand,
4 meters less than the rest of them during that time period. That's right. Exactly right. So you take the displacement of the plane, and you subtract the 4 meters displacement of the passenger during that time period, and you will get the overall displacement of the man relative to the ground. Now imagine trying to do this relative to the center of the galaxy. And that's what cosmologists do. Somebody asked me the question the other day about something about cosmology, and I said, I don't know, I'm not an expert. That's what they do. That's crazy stuff. So I try to avoid that stuff. So.
we wouldn't really know what the center of our galaxy is. It's theorized as a supermassive black hole. Are they for sure on that now? Or?
They have some very strong evidence.
Okay.
To be for sure It's
You'd have to send the probe there, which would take.
we certainly don't have time in anyone's lifetime to do that. The longest lasting probe we have out there in space right now has just barely left our solar system, and it was sent out 40 years ago. Voyager. Voyager 1, I think, is still going, but I don't think we're receiving telemetry from it. But Voyager 2, we're still receiving telemetry from, so and it was sent out 40 years
We're
ago.
not receiving telemetry from it, so it's just out there growing.
Yeah, it's because it'll just go until it runs into something. So there's nothing stopping it. So that's,
there's no way to get any of the data
yeah, it's run out of power. I believe it has. They may be getting something small back from it, but I can't remember.
okay, so it's run out of power, it's not like it's gotten out of range or something.
Yeah, it's because it's solar powered and it's way out of, it's just too far from the sun to get any solar power. So I believe the second one is nuclear powered. Well, they may have both been nuclear powered, but one of them we're not receiving telemetry. I don't know. I can't remember all the details. I could be wrong on both counts. But anyway, so we've got our displacement, we've got our distance now. We understand what those two are, what the difference is between them. And here's a nice little problem. I don't know if I gave you this one, but I like this diagram, right? Here you have the straight line distances, right? These are displacements, but these ones, these straight line distances, which are displacements, right? But these ones are distances that are much longer than the displacement because you turned and went backwards and then went forward again. Here you went all the way this way and then you turned around and went backward. So I just like that illustration of that. What time is it? 5:03. Okay. Let's do one more section and then we'll call it a day. So let's talk a little bit more about vectors and scalars and coordinate system. So they've already mentioned that vectors are this arrow representation of something that has a magnitude in a direction. Where did it go? They're changing this book sometimes without telling me, and they don't have the thing that I'm looking for anymore. That's okay. Let's go look at it's getting stormy outside.
Really glad when I see cars parked home at the
It's funny.
field truck.
Yeah, there's some thunder out there.
Well, I noticed.
On the chapter 2 questions, there's also only one attempt on all of them.
Okay, I'll fix that right now before I forget.
The second two questions, number 9, is has a part that with the two traffic two questions.
Yeah,
The Zuna nose and the number 9 question that I can't have.
okay. We'll take a look at that as well. Let's see. Chapter 2. Number 9. Address the
Where
displacement.
it says direction, it gives you all the
Oh.
initial direction.
Yeah, in this case, they're saying that the left is west and the right is east. So I will have that put in the problem as well. That may not be in it before you're done with the assignment, but we'll get that changed, get that fixed. Okay. I'm looking for a question that has there's a question where here's a nice one. So here we have a problem with two vectors. What are the two vectors that are shown in this problem?
The speed and the tailwind.
Yeah. So they're arrows. Remember that vectors are represented with arrows often. There's also a mathematical way to represent them, which we'll learn about. But in this case, we have the cyclist velocity and the tailwind velocity represented with arrows. Which direction are these vectors in?
Going in the same direction.
Same direction, to the right, right? Which one is greater?
The cyclist.
Cyclists, why? What tells you that's greater in the picture? What's that?
Longer.
It's longer, right? So the actual representation of the vector tells you this also. But also in this problem, they've said that one of them is smaller by 5 meters per second. Now, they haven't programmed this picture to adjust the arrows so that they're proportional, but they really should be kind of proportional. So if it's about half, then the tailwind velocity should be about half.
Mine says the cyclist is riding at 9 meters a second, and that the, here's in miles.
Meters.
And then it says that the tailwind is at 11 meters a second.
So yours is greater, so the,
Yeah,
so
the diagram, the picture is exactly the same.
yeah, so they haven't programmed that picture, obviously, and
That's how it should be.
yeah, and one of these days, they will maybe be able to do that. They would have to use some pretty fancy HTML5 programming to do it, but for now they've just pasted in the picture. So, but we do have two vectors, and that's important. But vectors can also be in different directions. So if we had a velocity of the wind that was going upward, right, then they would point up, right? And these vectors can add together mathematically and graphically. You could add them together. If these were actually representations of the cyclist velocity and the wind velocity, you could actually just add the two arrows together to make a longer arrow to represent the total velocity of the cyclist. Because the cyclist velocity might represent how fast he's pedaling, how fast he's making the bike go, but the wind might be pushing him even faster, right? So it just kind of depends on the problem, what you can do with these. But that's the power of vectors, is that it gives us a graphical representation of what's actually going on and allows us to visualize things and also to do things in 2 dimensions, because mathematics in 2 dimensions and 3 dimensions is not as easy as it seems. We are going to learn how to do it, and we'll find out that it's very doable once we learn how to do it properly. But it does involve, I mean, for 2 dimensions, two-dimensional mathematics is twice as difficult as 1-dimensional mathematics, and 3-dimensional is 3 times as difficult. That you have to do 3 times as much work, and you have to essentially do all the math in every dimension. So, but using the arrows, you can kind of simplify the process a little bit in many cases. So that is the idea of the graphical vectors. Now, what is a scalar? A scalar is a quantity that does not have anything but a magnitude. So distance, for example, is a scalar quantity, as opposed to displacement, which is a vector quantity. When we talk about speed, we're talking about a scalar quantity. The speed of something can only be positive. It's just a scalar quantity. However, the velocity is actually a vector quantity. So velocity requires you to know both the speed that they're going and the direction that they're going in that speed, the direction that they're going that speed. So anyway, oftentimes I'll use the terms interchangeably and try to correct myself. Sometimes I forget to. But you have to kind of keep your mind working so that you know whether we're talking about speed or velocity. It's just a common thing that we do in physics. We know what we're talking about, so we don't worry about it too much.
So
But
speed is a scalar.
speed is a scalar quantity. It only has magnitude. It only has a number associated with it, no direction. So let's say, for example, I'm going to McCook, right? And I travel there. It's 70 miles to McCook, and I get there in an hour. What was my speed? 70 miles an hour. What was my velocity? 70 miles an hour south, right? So,
The velocity is a vector.
sorry?
Velocity is a vector, but
Yes, velocity is a
you're
vector.
saying you use it interchangeably.
We sometimes speak that way, and it's very common. So just be aware that I'll make the mistake. I guarantee I will, and I guarantee you guys will. It's just we do that all the time. We do the same thing with distance and displacement. I try not to, but it just happens. So that's the difference between vectors and scalars, and we have to know the difference, especially when we're doing the math, because when you're doing the math with vectors, you're going to have to keep track of the direction that you're going, because it will make a difference in the answer that you get. So we're not going to go any further today, so I would recommend that when you start doing this homework for chapter 2, don't do anything that requires you to differentiate between speed and velocity or vector and scalar in any way, unless you're really understanding what you're doing, before we get a chance to talk about it again. This is kind of like our little preview discussion, and you can get started on some of these things and finish up chapter 1 for sure. But when we come back again on Monday, we will definitely do a lot of examples of these things, go over homework questions and how they're done, teach you how to work through these problems, and then I think this is due on Wednesday so far. We'll finish it up Wednesday, which we won't be meeting for live, but we will meet. Well, we may meet for it live early on Tuesday. So
will we know on Monday what the plan is as far as?
one of you wants to meet live on Tuesday, so I'll just go ahead and do it early Tuesday and record it. And then whoever wants to come early on Tuesday, I'll record it, and everybody else can just watch it on their own time.
How much earlier?
Well, what works? I would have to do it. We could do it in the morning. You want to do it in the morning, first thing? Or
Works for me.
9 o'clock or so? I don't like to do things in the middle of the day. I like to do things either at the beginning or the end of the day, so that I can use the rest of the day more efficiently. What's that?
My logic is the hungry king is boys too, so it doesn't overlap with lunch.
I just don't like cutting a big swath out of the middle of my day, and if I'm going to, I like it to be from 3 to 6, because that's the hot part of the summer. So if I'm going to be doing things inside, that's the time I want to do it, inside.
So what time did you say again?
Let's do 9 to noon on Tuesday, and we'll probably be done before that, but we'll discuss chapter 2 then, and we'll discuss the homework from chapter 2. We'll finish up chapter 2 on Monday. Tomorrow we will meet for a lab. We will have a lab tomorrow. I don't know if anybody's going out to Broken Bow tomorrow, so I'm going to have to figure out what I'm going to do tomorrow for Broken Bow. I will check to see if anybody's going out there and send some. I can send a piece of equipment out there if somebody's going out there. If not, then I will get it to you as soon as possible as this week. So hopefully Thursday or Friday. Sound good?
Yeah.
And I'll send the instructions. The lab for this week will be a movement lab. Essentially, you're going to have some motion detectors, and you're going to do a bunch of exercises with displacement, with distance, with speed, with velocity, and then next week we'll move on to acceleration. Well, next week we won't have a lab, but it will move on. It will go on to talking about things with acceleration as we move into the next chapters with force and other things. So we'll start off with, it'll be a kind of a vectors and scalars lab with actual movement and a motion detector. Any questions before we button it up for the day?
So when are you guys doing the lab?
We will do the lab tomorrow at the normal time. And like I said, I will try to see if anybody's going out to Broken Bow tomorrow, and if they are, I'll send the equipment with them and the instructions with them. If I can't get it out to you tomorrow, I will send it hopefully Thursday or Friday to you. And then you
Okay, can you send me an email?
Yes.
And let me know?
Yes, I will. I could maybe even just mail it directly to your home. If you want to send me an email with your address, I could send you a box with some of the equipment to start you off for the first couple of weeks, and then bring the rest of it to you later.
Okay. Yeah, and then when I was done with it, I just bring it back to the college here.
Yeah, that'd be fine.
Okay, that would be fine with me.
Okay, go ahead and send me an email with your address, and I'll get that in the mail tomorrow morning. Might be able to get it in tonight. I don't know if they've probably taken the mail already today, but I could definitely get it out there tomorrow morning. So.
Yeah, I'm actually talking to the people here. The one lady that I need to talk to is gone until next Tuesday.
Okay.
But I'm actually going to see if maybe we could use this Zoom Connect and I could just stay at home.
Yeah, you can definitely connect from your own computer with this, so that'd be fine with me.
So, but the lady's not here. They say they use it through the college server, so
Yeah.
they're not sure how it would work.
Well, I think it would be okay. But anyway, all right. We'll see you all later. Have a good night, and we'll see you tomorrow.
I have another question. Sorry.
Yeah. So go ahead. What's your question?
So when it comes to the questions that we put online,
Yep.
um, when you do miss something, but then you correct it, it still shows that like I did the bicycle one, and it was out of 3 points, and I got like 1, 1, and 0.97.
Yeah. It will take 3% of the problem for each attempt. Now, if you get it wrong because you entered it in and you didn't understand how to enter it in, or you misunderstood something in the question, just send me an email and I can fix that grade.
Okay, yeah, because with that bicyclist one, I typed in the direction was north and I put an N.
Yeah.
And it counted it wrong because I didn't put north.
Yeah, that's fine. Just go ahead and send me an email and tell me, and I'll fix it for you. Okay. And those are all things that we're going to try to clarify and make a little bit better as we test this class out. So it takes time.
It's not really that big of a deal, but
yeah.
Okay. Thank you.
No problem. You have a good one.
You too.
Steps here. And meeting. Do you guys have any other questions for me? What's that?